We've just seen a description of the HPPC method, the hybrid pulse power characterization method for determining power limits. And we enhanced it beyond what we saw in Chapter 1 by not only maintaining voltage limits, but also SOC limits and current limits and power design limits as well to make sure all of those were maintained. The predictions that this method gives us are still limited, though. The cell model that is used is quite crude, quite primitive, and it doesn't give us especially precise results. And at times there might be overly optimistic predictions or at times overly pessimistic predictions. If it's optimistic, that means that I'm over-predicting how much power is available, and that's a safety issue or a battery health issue. And if it gives a pessimistic value, it's under-predicting how much power is available, and that allows inefficient use of the battery capacity. So neither of those is desirable. We'd like to be able to use all of the capacity right up to the limit without causing any excess over the limit. Another thing these equations assume, based on how the resistances are calculated, that the battery is in an initial equilibrium condition, and that's not true in general because we're operating this battery cell quite dynamically. And so we need to, or we'd like to be able to refine the method to handle a more general case. If we aren't able to improve the method, I mentioned that we can use a derating factor or a trust factor to multiply the estimate by this value, say 0.9 for example, in order to hopefully maintain life, because we're generally more concerned with safety and battery health than we are about efficiency. If we had a better battery cell model, because the issue here is that the cell model is primitive, so if we had a better cell model combined with a maximum power algorithm that uses the cell model and also uses knowledge of the present battery cell state, maybe using a Kalman filter from Chapter 3, for example, we could improve that, and we could improve that, and we could get better predictions of how much power is really available. We are going to assume here a more accurate model in a discrete time state space form that is very similar to what we've seen already. So this is xn, n is the nth cell, so each cell has its own state equation. So xn at time k plus 1 is some nonlinear function of xn at time k and un at time k. Just like we've seen already, this model could be the physics-based model from the previous course, or it could be the enhanced self-correcting model that we use as the focus of this course. It's the same kind of state equation that we've already seen. And then the cell voltage at time k is some other equation based on the state and the input. So here I'm going to refer to the equations generically, but you can go back to Chapter 2 and fill in. It's like, oh yeah, that's the state equation for the ESC model, and that's the voltage or output equation for the model, and make that work that way. We will also assume that the delta t seconds of our prediction horizon can be represented as exactly k delta t sample intervals. That would not necessarily be true just in general, but it turns out to be true more often than not in practice, is that the number of seconds that I need to predict into the future is an integer number of sample points. So that's not a very limiting assumption. Then what we can do is we can use the model to predict the cell voltage delta t seconds in the future by taking the output equation here and saying, okay, the output equation k delta t seconds in the future, or k delta t samples in the future, is equal to h with the state that many samples in the future and this input at that point in time also. I can find this by simulating the state equation, this equation here for k delta t time samples with some input trajectory over that time horizon. And usually we're going to assume that the input trajectory u is constant over this delta t seconds when we do this. And so we'll just denote it as u sub n, the input to the model for cell number n. So if you think about this, I want to compute an input, which we've said is constant, so I want to compute a constant value for this. I don't know what it is. I want to figure it out such that this value hits some limit. And we do so by simulating this input through the state equation. And the state equation produces this value here. And, generically speaking, one way of doing this would be to simply guess what the input is and figure out what does that make the future state and what does that make the future voltage. And if it's too high, maybe I guess something smaller. If it's too low, maybe I guess something bigger. But I could somewhat randomly find this input. We'll look at a way of doing it that's not random. It's called a bisection method. That will be in the next section of notes, and show you how to do that in MATLAB. But it's a standard method for changing the input to a function when I'm searching for a specific output value. So assume we can find this value of u. Then to satisfy some equation, this is the equation that I want. For discharge current, I want to satisfy that the voltage of the cell is equal to Vmin, delta t seconds in the future, when I'm starting at the present state delivered to me from the Kalman filter, and I use this constant un input over that k delta t number of samples. I can rearrange that to set it equal to 0 because some of these algorithms are trying to solve an equation to become 0. The bisection algorithm in particular is usually described that way. When I'm looking at charge power, same idea. I'm looking for the constant value of u that k delta t samples in the future makes the voltage equal to Vmax, or rearranging to get this in terms of a 0. 0 equals the output equation minus Vmax. And that will give us the maximum discharge current to make a voltage limit for cell n, and the minimum charge current to get a certain voltage for sign n. When we are predicting into the future, we have to update this state here. And if we happen to have a state equation that's linear, then we can do this quite efficiently. And for our model, the ESC model, if we know the input current, I can create constant A and B matrices that correspond to that input current, and I can get an equation that looks like this. We know that xnk plus 1 is A times xnk plus B times unk is the general linear form. And if A and B are constant over the time horizon, as they would be for a constant current for us, we can get this form here. So the state of our model, k delta t samples in the future, is equal to the state of the model right now, given to me by the Kalman filter, multiplied by a matrix a to the k delta t power, plus this thing here, which is a matrix I can pre-compute, multiplying un. In fact, it's a vector I can pre-compute multiplied by un. This might seem harder, but in fact it isn't. It's quite easy. The A matrix in our case is diagonal, so to raise the matrix to a power, I simply raise all of the elements on the diagonal to that power. And also one of our elements on our diagonal is 1, and 1 to any power is 1, so I don't even have to worry about that one. And this one, as we'll see in the code in the next section, can also be computed quite efficiently, just doing a little bit of hand math first. So to compute the state a number of seconds or a number of samples into the future is not difficult. for the model that we have. And so it will be actually quite simple to do this bisection to come up with the value of current that will achieve these limits. The state of charge-based current limits are computed exactly as they were for the HPPC method, and we can compute power then as we did for the HPPC method, except when we saw this before and we said it was approximately equal to OCV minus IR, now we substitute in the much more exact calculation based on the full cell model, which is based on the present state, which may not be in equilibrium, and this more accurate prediction of the future. And the same here when we're talking about the discharge power. Both of these use the actual cell model to do it. They don't use a very, very simplified version like the HPPC method does. So all that remains is finding a way to compute U, the input current, into this model that will produce limits achieving the Vmax and Vmin. And we've already said that we're going to use a bisection algorithm to do that, and that is the topic of the next section.